Thank you all for coming. Mark Ito is gonna. So we've been working in this nice virtual environment, but this morning we're gonna start talking about, how to do things in real life, how to get your hands on the data, and Mark's gonna tell us about computing resources available at Jefferson Lab.
Let's see if this thing works. Okay, so Jefferson Lab resources. So the resources that we have here for doing computing. Friday the 13th. Yes. Okay, so outline, I'm going to talk about CPU, disk, and tape. All of this at JLab again. I'm going to take a sort of a side tour into a couple of the build systems that we have for compiling and installing your software, and then a little bit on getting help. Okay, so let's start. General purpose, this is the public computing around the lab. So just general purpose, so your standard web browsing, email reading type of activities. There's Linux, Windows, and the Mac option is there's no public Mac that I know of. But there's two platforms that are for this general purpose stuff. We have both Enterprise 6 and Enterprise 7. The lab is slowly transitioning to Enterprise 7. For Windows, there are in the CBAF Center. There's public computers up on the mezzanine above the cafeteria, and there's also if you have a Linux box of some kind, you can also access a virtual machine with this Windows Terminal Cluster server, and that's documented on the JLab Computer Center web pages. Okay. So that's general purpose. Now the batch farm. The farm itself is meant for doing big things, and it only supports batch mode. You have to submit a job to get your computing done. Right now it's Linux only. It runs CentOS 6.5. That's the distribution. The farm nodes are labeled YYNN, where Y is the year of the purchase, procurement, and N is, of course, the serial number. And right now, according to the Computer Center web pages, we have about 3,800 cores on 220 of these farm.jlab.org nodes. So there's a fair amount. Our estimate for when we fully come up is that we need about 10,000 cores, steady state, to prosecute all the jobs that we want to do. But we're a lot of the way there. There's a purchase plan for the end of the summer, early fall, and that will almost double that amount of computing. Okay. So again, it's batch processing only, so there's no direct log into any of these machines. You have to get to them to the submission. So I took Kurt Stroessel of the Scientific Computing Group took me down there and pointed out what was which. So this is allegedly a bunch of farm nodes, and so they're rack mounted. And if you zoom in, I think this is one node itself. These three boxes. I could be wrong about that. That's what I think. Anyone here know enough to correct me? Good. Okay. So this is what they look like. These are the 14 purchase series. Okay. So to get access to this, we have these interactive farm nodes. So these interactive farm nodes, there are very few of them. Actually, there are only 2 of them right now. They're configured to be exactly the same as the batch farm. So anything you do there testing-wise should be the same should have the same environment as when you come up on the batch farm. ifarm.jlab.org will automatically switch you to one or the other of these sort of randomly. to sort of load share between the two. So that's what you should be logging into. You get a direct interactive shell, just like your normal home directory. And like I said, it's meant to develop farm job scripts. So in particular, as far as environment, you have access to all of these scientific computing disks, which I'll talk about. There's a distinction. Some of our disks are available only on farm or iFarm. Okay, and but symmetrically between the two. And then there are batch farm submission commands. There's a JSub command, which is supplied by scientific computing that submits a single job. There's this Swift system for managing multiple closely related jobs. In other words, you want to analyze all the files from a particular run, or all the files from a particular run period. So it's only very minimal changes. So this has a database-backed system for managing all those, and John's going to talk about that, I believe. Okay, he's getting ready to talk about it right now. And there's documentation on the scientific computing pages. Okay. Okay, so that's CPU. Disk. We have general purpose disks. These are available both on the general purpose computing and on the farm nodes. Home is your standard home area. We all start out. New users start out at 2 gigabytes. 2 gigabytes. Okay. I think that's true still, isn't it?
Yeah.
Right? Yeah. So very stingy. So what you should do, the first thing when you log in your account is you send a request to the computer center for more disk space in your home area. And usually that's kind of granted, within reason. So if you ask for a fixed percentage, year over year, of course you grow exponentially as time goes on. Never mind. But you can ask for more.
What is a reasonable request?
Oh, I always ask for 20% every 6 months kind of thing. Well, I mean, okay. That's kind of joking. But anyway, the point is it's fully backed up. Okay, so they do nightly incremental backups, the weeklies, the monthlies. You can go, but allegedly you can go back years, right, and get any file from any day of any year, in the past. So it's fully, completely backed up. And it's also what they call snapshotted. So there's a way you go into this magic directory, this .snapshot directory, and you get an image of your disks. An hour ago, 2 hours ago, 3 hours ago, yesterday, the day before, last week, the week before, kind of thing. Okay. So it's expensive actually. So because of all of that, it's expensive to maintain this disk, and that's why they don't want to give out very much. Okay. So that's home. That's the norm. That's what you think of your normal home area. Okay. Snapshotted. Group is also backed up. It's also snapshotted. And for Hall D, we have a whopping 600 gigabytes of space on this. So this is meant for stuff that we share as a group. Okay, so in particular, documentation, the builds of the software that are supposed to be used by everybody get housed here. This is not very much. So in particular, you are discouraged from putting data on the group disk. Okay, that's for other things. This is really for this kind of stuff. The wiki is housed here. Hall D Web gets all its files served from this disk. Okay, so just for completeness, there's also apps and site. Apps are really for computer center installed versions that are not coming with the distribution Red Hat Enterprise. So we have newer versions of, for example, GCC and Python and things like that. More modern than distributions. Those will show up on apps. And site is for really the JLab centric type things like go to site bin, you'll see the the staff command for looking up people, what their phone number is around the lab. Okay, and then there's also Scratch. Scratch is a little bit shy of 5 terabytes. This is not backed up and it's auto cleaned, so any file which is 2 weeks unaccessed just gets deleted. Okay.
Isn't that /u/scratch?
There's several.
Okay, well,
Confusing.
it is confusing. I'll get to that. This is /u/scratch actually, but purpose of this talk, I was not going to spend 10 minutes explaining Scratch. Yeah. Anyway, okay, so that's general purpose. Now this is the scientific computing. So this is what I was referring to as the farm and the iFarm only. So we have work, MSS, which isn't really disk, cache, volatile, and then there's local Scratch. So this is the other Scratch, which is different than the Scratch that I had before, right? So that should tell you something that it's confusing. Okay, so for work, this is the large work directory. So this is where you do your work, basically. Okay, we have so large data files, personal builds of the software, because you would really like to do this in home, but home is so small that we're kind of forced by the way they have configured things to do code development and builds in work. Okay. All right. So that's not ideal. Work is not backed up. Okay, so you have to be cognizant of that. And one thing that brings that even lately makes it more important is that our main 115 terabytes, which is a good chunk of disk, is mounted under /work/hald, and that is Lustre. And the Lustre service that we've been running for the last couple of years has been problematic. And we actually have had instances where files have been corrupted on that thing over the past in the past 6 months, especially. And they're working on that problem. It's high on their list, but so far we do not have a solution. I mentioned this at the collaboration meeting. So, be careful about what you're doing here. Because of these problems, we have asked for another work disk, work-hald, which is much, much smaller, but is used as traditional RAID system bought several years ago. Okay, and this is and we've never lost a file over many years of using it. So the idea here is for right now, especially if you're doing code development, you probably want to do it on hald 2 until the situation changes. And in addition, there's a structural problem with Lustre, and the small files are not handled very well, kind of slow, and SQLite database files don't work at all. They're stored on Lustre. Okay, so for that, we probably will need this traditional RAID going forward as well. Okay, /MSS is a huge directory tree. It's basically a representation of the tape library. I'll say more about that when I talk about tape. So you can imagine a huge directory full of sort of pointers, basically. We call them stub files that mark where the represented file actually exists on tape. But if you wanted to browse through all the files in the tape library, then you can just browse through this directory. Okay, cache is where you do the actual realization of MSS. So cache will have many, many, many fewer files here, but the files will be real files. Okay, you cannot, of course, move everything out of the tape library onto disk. And for hald, 35 terabytes of this can be pinned. Okay, so what happens is this cache, since all the files in cache actually are on tape. Okay, so they come sort of pre-backed up. Therefore, when cache gets full, they start deleting old files, unless they're pinned. So you can say that this file is important to us. We want it to stay on the cache disk. We want to be using it for the next little while. It has to go with a files will age out. Old files will get deleted. Okay, volatile is basically another scratch disk. This is also Lustre. Our allocation on this is 20 terabytes. We can go over that whenever we would like, if there's extra space on the disk at that particular time. Those files will be that are over our 20 terabytes would be subject to a cache-like deletion algorithm. But anything under 20 terabytes is guaranteed to stay there.
So, but work halt D, but we don't have 115 terabytes for ourselves, right?
Yes, we do.
Oh, we do?
Yes.
Whoa, okay.
That's for us. I remember when we first announced this, we didn't. The sky was the limit, right? Because they hadn't worked out the quota. I know this is the quota now because of Sandy's email. If you look on the pages, it won't tell you what the quota is. So now they've got to the point where they've actually imposed a quota, but they haven't got to the point where we can tell what it is. So, you know, it takes months to do these things. But you know what? I checked her email this morning because I was thinking 115 terabytes sounds big, but that's what it said. Okay, so that's cache. So this is the realization of the tape library. And volatile is temporary storage. Old files are deleted to make space for new. So you know you can write this forever. And then there's local scratch. This local scratch is called /scratch, but it's the farm and iFarm only. But it's different from the scratch general purpose. And so the way you tell if someone is a real veteran of JLab computing is if they can tell you the difference between scratch. They can explain that to you. Then they know what's going on. Okay? You can use that as kind of a test to see whether you should believe what the guy's saying, you know, kind of thing. Okay. Tape. Okay, so we have this tape library. According to Computer Center, we have 10 petabytes of data in there now. Okay, so the tapes are tapes. They don't look exactly like this, but you know, what am I saying? Paradigmatically, they're exactly like this. Okay, so there are frames, which I'll show you in a second. There are slots in the frames. This is the sum over all frames. Disk drives, 10 plus 6. LTO5, LTO6. 6 is the next generation after 5. Throughput's about the same. The disk, the capacity is bigger for the LTO6. Raw means that there's also the data movers do compression on the way in and decompression on the way out. So this is presumably without any compression.
How large, by the way, is the data written to tape now on this last run? It's about half a petabyte.
Half a petabyte. Half a petabyte. So we just had a 5%.
I mean, I think that, you know, we were guessing that we're supposed to generate like a petabyte or so a year.
A petabyte a year was kind of the round number that everyone remembers, you know, kind of thing. Which means it's, you know, it's wrong at some level. But what we did was consistent with that. And this is what's being stored. I think the capacity is 20 petabytes right now. The other thing that happens, since you asked, is that as time goes on and this new technology comes along, historically at the lab, we've always taken the low density stuff and written it to high density stuff. Okay, the shelf space for these two technologies is exactly the same. The form factor of the cartridge, you know, they're standard cassette, you know, kind of thing. And so what happens is that as you go to a new technology, if you do that copy, you free up space, you free up shelf space, right? And they've always done that, and we've always been in a position where we never really had to make a hard decision about what to reject, you know, to make space for new data.
So we can go back all the way to 1995?
I believe so. I think there's some stuff that was ejected, I think, at some point. But remember that going back to the beginning of time, or 1995, whatever you want to call it, the technology was completely different. It was a storage tech. It was a cylindrical room. Okay, this one you'll see is rectangular. Okay, so it's pretty different, you know. So even from 10,000 feet, it looks different, you know, kind of thing. But we just kept copying forward and forward, right? And been able to always do this. So that's kind of a nice thing. And I think there's a new generation, you know, waiting out there, LTO7. I believe, if I'm not mistaken. Okay, so remember the MSS directory I talked about? I kind of said this, but you can think of this. This is not strictly true, but you can think of this as a huge directory tree. The one-to-one correspondence between these stub files in the directory tree and files on the tape. Okay, the structure on the tape, of course, is nothing like the tree structure that you'll see, or is only very loosely related to the structure on tape. The main organizing principle are these volume sets. So you can think of that as a virtual shelf of tapes, such that when you put a random file into the tape library, it's actually directed to go to a particular shelf. That way you don't have, you know, your data file and then, you know, the undergraduate students' Word document sitting on the same tape, kind of thing. So when you're accessing your data, you don't have to wade through the undergraduate summer students' Word documents to get to your valuable data. So that's kind of a detail that you really don't have to worry about very much, but it's there. Okay, so that's tape. This is what it looks like. So don't tell anyone, but I had to open this door in order to take these pictures. I'm not even allowed in there. I had to like sneak in and hide. No. Kurt Stroessel took me on a little tour. He let me in there, and he removed the door graciously. So you can see this is your standard computer tile. So you can see that there are these sort of cabinets as you go down. I think those are the what are they called? Frames. Those are the frames. So there are allegedly 9 of these going down there, and if you walk up to the door and look in, you see a bunch of tapes on shelves. And if you look at the ones on the end, you stick your head in there and you see the cartridges. And then if you look very carefully, you'll see it, I think, a little bit later, but there's a row here where there's kind of a hole in the shelving arrangement. That is, that panel is full of tape drives. Okay, so you can add tape drives to the system sort of arbitrarily at the sacrifice of a little bit of tape shelf space.
That accelerates access then, if you have more drives then? What's the deal with having more drives?
Yeah, sure. Right, you can be streaming more, you can be reading more data and writing. You could have more streams going at the same time. Because each of the drives is connected to a separate, what they call a data mover, but just a computer. Right, so you have one computer, one drive sitting and go independently. Okay, so this is the first time I've ever done this. Okay, so you guys think this is easy, but this is really exciting. So cool, huh? That's very nice, huh?
How many features do you have in this?
Okay, this only goes for about 2 hours.
So you're telling me most of the time it sits around doing nothing?
Well, it's nice. It's
Oh.
Wow. It's running. Wow.
It's confused.
Okay, there's actually sound on this. You can hear the thing. And you can hear me at the beginning saying, why isn't it moving?
Did you slow that down?
No, well.
Because I saw that at open house and it went way faster.
I didn't slow it down intentionally or anything, but Anyway, so what's the point? The point is, if you, this is on YouTube, by the way. If you watch it again, what we saw was it was parked in the beginning in front of the wall of tape. Okay, and what my guess is that it pulled the tape out of one drive, went and deposited it. That's why the stoppage there. And then it went to get another tape, right, at the far end, and brought that back, stuck in a drive, and parked there in front of the wall of tape. So, yeah, someone mentioned that they thought that MSS was just a bunch of soft links, and why did it take so long to get the data out of off of tape?
How long does it take? So if a tape file has to be dumped to the cache?
Well, yeah. So basically, you can see that the access is not terribly slow. It's just not. You see, most of the time when it's sitting there, what's happening? Those tape drives are working, right? They're either writing or reading. Okay, it's just not time to change tapes. It's not like it's working continuously. But the other thing is, oops.
Next.
I don't know. I'll go back. Go back a couple. I don't know what happened. Maybe this thing is running out of batteries. You can go back another one. Oh yeah. Okay. So here's the intrinsic bandwidth. Okay. But the speed depends on a lot. Depends on how the files are arranged on tape. You know, because if you were to have a bunch of doc files in between your data, it would slow you down, right? And if you're asking for runs here, okay, that's going to be very slow. And so there's a big dependence on just your. So it actually pays a little bit to think about how you write your stuff to tape. You want to write similar files. You want to actually collect a bunch of similar files and write them all at once, so that when you go back to get them, they'll be right next to each other, and the tape head won't have to slow down, skip, and whatnot. It's like the old days. They used to. Never mind. I was going to talk about drum memory, but never mind. Okay, this is back working. Okay, so now the side road into the build systems. So what do I mean by build system? There's this basic problem. We have a bunch of packages, software packages, Jana, HDS, Xerxes, CernLive, Root, Jan Fork is coming on. These all have different versions, okay? And if you're building them yourself, you can arrange them in many possible, there's an infinite number of directory structures that you have. Okay, so the build system is trying to orchestrate all of that. Some versions of some of these will not work with certain versions of others of these. We're doing this ourselves, and we're going forward. We have multiple data sets in different times, projects starting at different times. They may want access to an older version of the software. The newest software may break something that you are doing personally because you're not ready to quite update yet. So it's a very complicated terrain. Linux distributions, for those who've done that, you get one set of versions, and they say that one works, and that's the one you deal with. So in this case, we have this multiplicity in the version dimension along each of these axes to deal with. Okay, so that's a standard problem. So, like I said, the directory structure, it has to provide help building each of these and some way to manage the versions. We have two build systems. One is build scripts that I maintain, and the other is the Haldy package manager that is maintained by Nathan Sparks. Nathan, raise your hand. Stand up. There you are. There's Nathan. Okay, so unfortunately for Nathan, they asked me to give the talk. This is going to be perfectly unbiased and everything. I'm not going to throw aspersions on Nathan's fine work, but they're developed. They're similar and different at the same time as is anything else. Okay, so here's the build scripts. Here's the HDPM. This has a fixed directory structure, although other structures are accommodated, but it will impose this directory structure on you by default if you don't say anything. It's based on make, so you have one make file per package with a package with those things, HDDS, Jana, etc. version number is an input to the make file. And they're communicated via the environment, and there's an XML configuration file to drive these environment definitions. And the same XML that is used to drive the build choices can be used to set up a user environment to use those builds. Okay, and by having these XML configuration files, you can define the combo, the working combination, and communicate that to your colleagues. Okay, Haldy Package Manager, you have basically the same features. Specifies a list of paths to SimRecon and all of the other packages that SimRecon needs. There's a set of text files to configure this. I believe it also works with the version XML, or at least that's if that okay, yes. So you can cross this configuration from one system to another based on the Julia programming language. There are additional commands for downloading stuff to start up the build, to update a particular package, and for cleaning them. Just if you want to start over. And the other thing that is not supported by build scripts is you can use this system to install precompiled binary packages, both Linux and Mac. So Nathan maintains that for several Linux distributions as well as Mac OS. Ubuntu, Fedora, CentOS, is that right? Okay. Okay, here we are practically at the end. Okay, how to get help. So this is a list of wiki pages and email lists. So the first one is the GlueX analysis wiki page. So that one looks like this. So there's how to set up and do an analysis. So there's not only is there a listing of all the things that is known that we are working on, but at the top in this section, there's a bunch of links to information about the kinds of things that you've been seeing in the demos and exercises that we've done during this workshop. Is that fair to say? Okay, so Paul likes that. Justin's not complaining.
There's a link to that page on the main wiki page. It's right on the right column.
Okay. Notice that this is in the private wiki. I mean, there's a lot of computing type stuff we could talk about, but
Yeah.
you could finish.
Yeah, maybe one thing to mention about that is that to get the private wiki, you have to have a JLab account. So,
You have to have a JLab account, and you have to be part of the Haldy group.
oh, right.
So, on and on. There's all these little local things you have to know. But anyway. Okay, so back to here. There's the offline software wiki page. This has package documentation. There's a set of how-to pages that are linked to. All the meetings have minutes recorded here, and this is the URL. That one looks like this. So, general information, The news is a little bit out of date. This is right about when I had to start being a run coordinator. But anyway. And if you scroll down this page a little bit, here's the software packages. SimRecon, the tagged releases. Jana has its own web page. HDDS is the geometry. HDDM is the data model for using for Monte Carlo and for REST files. EVI, CCDB, RCDB, all the buzz names. There's a collection of links here. AmpTools is linked to. Okay. The next thing is scientific computing pages themselves. So these are maintained by IT division, the scientific computing department of IT division, I guess you would say. And that looks like this. So you have the farm users guide, link from the top page, and you have experimental physics user portal. So this is where you see the list of all the jobs that are running and views look like. And this of course is documentation. Okay, and then finally there are these email lists, Haldy offline, Haldy physics, GlueX software, and then these simple lists. So go through those very quickly. Haldi offline. See the about Haldi offline is really informative here. But basically, this is for all the sort of computing, software, offline infrastructure type discussion. Like what compiler are we going to be using? You know, the new work disk is broken, kind of thing. So that's what that is, and then Haldi Physics has an equally enlightening about section here. This is discussion about ongoing physics analysis and conferences that are coming up. So things really related to the physics business. We don't have it. Well, anyway. Okay. So these are hosted at JLab. These are our main email lists around this area. And then we just started this GlueX software help. It's a Google group. There's various discussions. So this is probably a little bit higher bandwidth and a little bit lower level. And you know, the welcome message says simple questions, tough questions, proposals, ideas, suggestions, discussion. So this is sort of a catch-all. Anything that's related to GlueX software, you're allowed to ask here, and threshold expertise needed to participate is meant to be as low as reasonably achievable. Okay, so that's that. Then there are these simple these are a bunch of notifications. This is one-way communication from the cron job to you, basically. Yeah, but you can subscribe to be on the list of hearing from the cron job. So different things. We do a nightly build on four of the operating systems. We do a test of B1 Pi from generation to simulation to reconstruction, and histograms are created, web pages are created. We do that twice a week. There's a test for single track tracking. We just throw a Monte Carlo single track into the detector. CCDB, the calibration database changes every day. This gives you a list of what's been going on the past 24 hours. Git repositories. This one was instituted very recently, so this will give you a list of monitoring, send you to a page full of monitoring histograms for all runs that we collected just recently. So this list is turned off right now because we're not running. But we had it on towards the end of the run. It's just
That was very useful, by the way.
good. Good. Oh, and if people have other ideas about things that they want to send out on a regular basis, remember it's subscription based, so you're not sending it to everyone. You can send it to just your friends or whatever you want. I can help you with the setup. Okay, so that's the list. Okay, so the last slide. So we do have this stuff here at the lab. I showed you the two build systems, build scripts in HDPM. What I didn't tell you is how to actually use any of this stuff. So sorry about that. But I've already talked for my time, and I haven't, by leaving all that stuff out. So you're going to have to, ask people or go to those help resources to find out more of the details. I just wanted to give you a taste of what's available here and what the different intention of the different pieces are. Okay, thanks.
Hopefully Sean will show us how to do some of these things.
Yeah,
Aaron was
not
next.
all of them.
Thanks, Mike.